be talking to us about the work that was done with this HARM3D code.
Yes, so I'll try to be minus 20 minutes long, and yeah, so I'll be quick. So the punchline is that we're still working on getting this to work.
You can use your 10 minutes, that's fine.
So the we've got a general relativistic magnetohydrodynamics code that simulates accretion onto two black holes in orbit around each other. So we don't do the numeric relativity evolution, but we use a perturbative solution to Einstein's equations, which essentially results in us having to call this horrendous function to give us the space-time metric, or the gravitational potential of our system. And this is a rather costly endeavor, and that function call is, and it's not uniform across our volume. So it's more expensive near the black holes than it is far away from the black holes. And so this amounts to a rather obvious load imbalance. And so instead of rolling our own, so this was a pretty simple load imbalance, and we could have probably implemented a simple load balancer solution inside of HARM, but we are also developing this patchwork code that will give us rather heterogeneous communication patterns. And so we were hoping that we could use this experience to also load balance the patchwork code. So this paid project was going to allow us to get load balancing experience using AMPI, the AMPI tool, which is a charm++ derivative. So it's like it uses the charm++ code, but uses it in a way that it doesn't require the user to rewrite the code in the charm++ language. So pretty much you plop in calls to AMPI routines, and you have to then maybe label some variables that are dynamic using these directives, these thread directives, if it's a mutable global object. And that allows you to pretty much use the load balancer right away. Now the usage of the thread local storage aspect, those directives, wasn't sufficient for our data structures, and so we had to actually pack and unpack the data structures. So the idea is that you've got all the grid functions in your memory, and those have to move. Those define what the local processor is doing. And that local processor may actually move physically, so that's a virtual process. And that virtual process may move to a different physical process or processor. And so you have to encapsulate the memory into this object that is then migrated. So the user has to write this routine, the pack-unpack routine that does this parceling. So that's pretty much what we had to do, and we had to also rewrite all of our global variables. So we used a lot of global variables. I know it's a bad thing to do, but we did. We had it before, and so now they're all encapsulated in a global structure. So this helps us pack and unpack. In the future, we may go to a full charm++ implementation, but we haven't started doing that yet. I know there are other codes that are similar to ours that are doing this, the Spectre code, and they see great results. So that's encouraging. So again, the basic idea is that, so this diagram in the lower left shows you a schematic topological representation of the different domains or zones of our space-time metric calculation. So each black hole is identified by these black dots, and then there's a local gravity solution that we use that's really expensive right near them. But then there are these buffer zones that transition between the different solutions, and in those buffer zones you have to use the inner zone, the one close to the black holes, the inner zone metric, and the near zone metric, which is just outside the black holes. And so you actually have to use, so inner zone is 3 times as expensive as the near zone, but in the buffer zone, you have to evaluate the inner zone and the near zone metric. because that's the transition region. So you're kind of interpolating between the two solutions. And so those buffer zones are actually really expensive. They're 4 times as expensive as a near zone calculation. So we've measured this difference in runtime performance in the metric, this black curve. So these are timers. This plot shows you how much time a given process spends in a given set of routines. So this black curve is the metric evaluation. So you see that about half of the processes are it doesn't take very much time to calculate the metric, but in the other half, it takes 3 times as much. So this is the load imbalance that we measured it, and the metric can take up to 84% of the runtime. So that was our baseline performance measurement. I just want to outline, before I give you the some results, an outline of what we've been doing. We had an in-person visit. So Spencer James was a senior graduate student that was working on this project at the University of Tulsa with me, and he was a principal developer and performed most of the tests. And he visited the group at University of Illinois, and we also maintained pretty good contact. So Sam White was our principal contact in the CHARM group, and he was very responsive and very hardworking, and has answered all of our questions. So we're very grateful for the team and helping us figure out how to use AMPI. And also, I think we're one of the first groups that used HDF5 with AMPI. And that presented a number of issues with AMPI, and so pretty much we're dealing with this out-of-memory problem. So when we actually deploy a production scale run with AMPI, when you write more than one HDF5 file, it exhausts the memory pool, and so we're trying to figure out what's going on there. But so since we couldn't deploy this at full scale, we wanted to see in principle if this was going to work. And so Spencer did a test on a single node. This is a kind of an old test. We can go to hundreds, like maybe 100 node run without suffering this problem immediately. So it's not like we can't go more. You can't use more than one node. But anyway, we're focusing on debugging and not really scaling performance right now. So I just wanted to highlight the fact that even on the simple simulated load imbalance run, so this was using a simpler configuration of HARM, so it's not a binary black hole simulation. The binary black hole simulation requires a couple hundred nodes to run. So since we had to fit it on a single node, we had to use a single black hole accretion disk run. And so we simulated the load imbalance by just having some fraction of the processes do more loops. Okay, so, and we found, we measured the number of steps per second the simulation took. So these are full domain time steps. So the faster the rate, the faster the calculation is proceeding. And this is versus virtualization ratio, which is the number of virtual processors the number of virtual processors per number of floating point cores. So we found that we also did this for a number of load balancers. So this cyan curve is the greedy load balancer, and the magenta is the I forgot what it's called. I can't read it. Refine. Oh, right. The refined load balancer. And so we see, I guess, the greedy one works better, and also using a virtualization ratio of greater than 4 doesn't really help us. So at least for this particular test. So we'll have to repeat it for our production level run, but we got a 40% speed up at that maximum rate. So that's encouraging. And I think I can't see this not really working. And we also measured the overhead. So even at this rather unintensive calculation, the overhead between running without AMPI, which is this red circle, and running with MPI, which is, you know, this magenta and blue point, there's not much difference. So we're not penalized by using AMPI too much. So that's encouraging. And other benefits that we've accrued from this project is that we've cleaned up harm pretty well. So that's our GRMHD code. So all the globals are nicely encapsulated in a structure, and we've removed a lot of cluff, garbage in the debugging process, and in order to narrow down the areas where it could be a problem. And Spencer James learned a lot about load balancing and debugging and profiling. And yes, so thank you.